Hey there, class. In this lecture, I want to talk about deductive reasoning and biconditional statements. This is Chapter 2, Sections 3 and 4 in your book, if you're following along. And I want to dedicate this lecture talk to Max Pfeifenberger, who on Friday said to me while we were having a lecture on inductive reasoning, he said, "What? You're gonna actually teach us?" And I just thought that was really funny. So Max, this is for you because, yeah, welcome back. It's like the Matrix where you're going to plug in right now and you're going to process and download all this information. So, yeah, we're back to the virtual blackboard. Okay, what are we doing here? We're talking about the law of detachment, which many of you are detached, so that's just perfect. And syllogism, and no, that's not something to laugh at every time you say it. But we're going to explain what syllogism and detachment are with regard to deductive reasoning. And then we're going to jump into biconditional statements, and they'll make a lot more sense as we go along. So take a look at this question. Is the conclusion a result of inductive or deductive reasoning? Well, inductive reasoning, as we've already learned, is using observation. And deductive reason is using logic. It's something you can't directly observe, but you know is true based on the use of logic. So here it is. There's a myth that you can balance an egg on its end only on the spring equinox. A person was able to balance an egg on July 8th, September 21st, and December 19th. Therefore, this myth is false. So the question is this conclusion a result of inductive or deductive reasoning? Well, since we observed it, somebody did this, that is inductive reasoning. Now take a look at this example. There is a myth that the Great Wall of China is the only man-made object visible from the moon. The Great Wall is barely visible in photographs taken from about 180 miles above the Earth. The moon is about 237,000 miles from Earth. Therefore, the myth cannot be true. That is an example of deductive reasoning. We're not going to the moon, looking for the Great Wall and say, "Oh, wait, we can't see it." No, we're saying, if you can't see it from 180, well, you certainly can't see it from 237. So that's the main difference between inductive reasoning and deductive. Again, inductive using observation, deductive using logic. In deductive reasoning, of course, if the facts are true and you apply the correct logic, then the conclusion must be true. So the law of detachment is one valid form of deductive reasoning. And how it goes, and this is in your vocab sheet if you're filling it out. If P, then Q. If that is a true statement, and P is true, so you supply a true hypothesis or scenario, then the conclusion is also true. And I'll show you what that looks like here in a second. "Oh, master, is it proper for a monk to use email?" Sure, as long as there are no attachments. Okay, try this one out. Determine if the conjecture is valid by the law of detachment. If a student passes his classes, the student is eligible to play sports. Many of you can relate to this. Ramon passed his classes. Sounds reasonable? Therefore, Ramon is eligible to play sports. This is valid by the law of detachment. If this statement here, if this conjecture is true, and Ramon has passed his classes, true, then this, of course, will take place. And that's what you've been doing every time you argue with your friends. You're saying, hey, let me provide another example. So another form of deductive reasoning is called the law of syllogism. And I like to think of this as like the transitive property, and we'll get back to that, or we'll jump ahead to that in a little bit. But what this does is it allows you to sort of skip over a step. And it allows you to draw conclusions from two conditional statements when the conclusion of the first is the hypothesis of the second. So when you have your vocab sheet, you'll see, right, oh, if P then Q and Q then R are true statements, well, naturally, if P then R is a true statement. So what in the world does that look like? Let's take a look. Penguins are black and white. Some old TV shows are black and white. Therefore, some penguins are old TV shows. logic. Another thing penguins aren't very good at. No, let's try better. Okay, determine if the conjecture is valid by the law of syllogism. Let me pull out a little highlighter here, and let's just highlight some of these things real quick. Okay, so if a figure is a kite, okay, then it's a quadrilateral. All right, seems to make sense. If a figure is a quadrilateral, then it's a polygon. Oh, so this is a great example of the law of syllogism. Conjecture, if a figure is a kite, then it's a polygon. So here's how it looks. This is P. If P, then Q. I'm going to just put it over here. Of course, it's the whole green thing. But then, if Q, then R, right? And so what we're really saying is, this is my P, if a figure is a kite, then R. See what I mean? So we're jumping over this whole Q part, right? Q is the conclusion of the first statement, then it is a quadrilateral, and it's also the hypothesis of the second statement, if the figure is a quadrilateral. So it's a way to kind of connect the dots, or you might say it's a train of thought. Please make sure you're getting syllogism and law of detachment into your notes. I'm going to be coming to look for that as part of your assignment. So here it is. We've already spelled that out. Let's just move on. So now let's apply the law of detachment and the law of syllogism in logical reasoning. Okay, is the conclusion a result of inductive or deductive reasoning? Question 1. At Reagan High School, students must pass geometry before they take Algebra 2. Emily is in Algebra 2, so she must have passed geometry. What do you think? Inductive or deductive reasoning? When we meet in class again, I'm going to be looking for your answer, and then we'll talk about it then. Second question I want you to answer is, determine if each conjecture is valid. So given if n is a natural number, then n is an integer. If n is an integer, then n is a rational number. So if you need to look up what rational and natural, all these things can be found on the Venn diagram lab that we did in class on Monday or Tuesday. But anyway, what we're saying here is 0.875 is a rational number. Okay? Conjecture, 0.875 is a natural number. Based on this sort of logic or reasoning, is this conjecture true? Is this valid or not? Put your answer in your notes. I'm going to come around and we'll check it in class when we meet next. Okay, so that was section 2.3. Seems pretty easy, only took 8 minutes. Now, let's talk about biconditional statements. When you combine a conditional statement and its converse, you create a biconditional statement. So it's a statement that can be written in the form of P if and only if Q. And what this means is if P, then Q, and if Q, then P. It means both. It means absolutely both. So you can write it like this, P double arrow Q, which means if P, then Q, and if Q, then P. You're going to see this a number of different ways, but primarily you're going to see this if and only if, or you're going to see this double arrow as a biconditional statement. Okay, here we go. Let's try it. Write the conditional statement and converse within the biconditional. An angle is obtuse if and only if its measure is greater than 90 and less than 180. Okay, sounds reasonable. So let's write the conditional statement. Conditional statement is, if an angle is obtuse, then its measure is greater than 90 and less than 180. All right, so what would you say the converse of that would be? Okay, well, the converse, if an angle's measure is greater than 90 and less than 180, then the angle is obtuse. And what do you think? Those are both true statements, right? So this is a true biconditional. So try this one. For each conditional, write the converse and a biconditional statement. Ooh, okay. So we're going to write each conditional write the converse, and a biconditional statement. So if 5x minus 8 equals 37, then x equals 9. What would the converse of that be? Well, the converse would be if x equals 9, then 5x minus 8 equals 37. And a biconditional statement. So we could say x equals 9 if and only if 5x minus 8 equals 37. Or you could write it the other way around, but that would work. Let's try another one. If two angles have the same measure, then they are congruent. I want you to try this one. What I want you to do is write the converse of this statement and then write a biconditional statement in the form something if and only if something else. And I'm going to come around and check that in your notes when we meet next. All right, so for a biconditional statement to be true, its converse and the conditional statement must be true. If either the conditional or the converse is false, then the biconditional is false. So here it is. Determine if the biconditional, two angles are complementary if and only if they are both acute, is true. If false, give a counterexample. Okay, well, can you think of any angles that complementary means adds up to 90, two angles that add up to 90? Okay. Two angles are complementary if and only if they are both acute. Okay, so that's true, but what about the other side? What if you said, okay, if I have two acute angles, then they are complementary? Well, that's not true because, hey, I've got an angle that's 37 degrees and an angle that's 32 degrees. Okay, and those two are definitely not equal to 90, which means this biconditional statement is false. Okay? In geometry, definitions are always biconditional statements because what we can do is we can look at a definition, and the definition describes the term, and the term is the definition. Does that make sense? I'll show you what I mean here. A triangle is a three-sided polygon. True. A polygon is a three-sided triangle. True. Biconditional statement. A figure is a triangle if and only if it's a three-sided polygon. And the same would be true for a quadrilateral. So these are definitions. The conditional statement is true, the converse of which is true, and when they're both true, it's a true biconditional statement. So last thing to think about, definitions are reversible. Postulates are not necessarily true when they are reversed. That's really all I had in this lecture. It's really two lessons in one. When I come around and check your notes, I'm looking that you have law of detachment, law of syllogism. I'm looking that you have tried to answer problems 1, 2, and B. And so those were the 5 items or 10 points that I'm looking for when we meet together in class. If you have any questions, you can drop me an email. Otherwise, write them down, save them for when we meet next. And Max, I hope this worked well for you.